This next lesson will talk about the evolution of concurrency and parallelism in Java over time. If you know much about the history of Java, Java first came out in the mid-90s. It was available before that for internal use at Sun, but it was released in 95, 96 timeframe. You may know some of this stuff, but unless you've been really a student of the history of Java, some of this may be new. So let's talk first about the history of concurrency support in Java. So when Java when it was first released in 95, 96 timeframe with JDK 1, it supported right out of the box basic threads and so-called built-in monitor objects. So Java's always been focused on concurrency, even though back in those days there really weren't a lot of parallel processing environments. We had single-core computers, really. Multi-core didn't really start showing up more to the middle 2000 timeframe in commodity systems. These foundational features supported basic multi-threading and synchronization primitives. Here's a very simple example, not unlike your programming assignment. This example creates a bounded blocking queue, and then it creates two threads. One thread will produce data and enqueue it into the simple blocking bounded queue until it fills up. And the other thread will sit there and read data out of the simple blocking bounded queue until it's finished. And if there's nothing in the queue, it'll block till there's something there. So it's basically classic producer-consumer style problem. Once we create those two threads, we go ahead and start them. So you can see here we're going to go ahead and start the threads. That's very similar to your programming assignment. And then we're also going to go ahead and once they start, they're going to start running and doing their thing. And then this piece of code will wait for the threads to finish. A couple things to note, just because I saw some code today in office hours. Always make sure when you create a thread, you give it some computation to run. Here, for example, we're giving it a producer and a consumer. Never say new thread, open, close, paren, because now you're creating a thread that has nothing to do. So it'll do nothing, and you'll be wondering, why does my program not do anything? Well, it's because you didn't give any work to do. Likewise, once you start the threads in your assignment, one of the threads, and it's pretty easy to figure out which one when you read the assignment, is going to have to wait for the other ones to finish. And that'll do something sort of along the lines of this, although you'll have to do a bit more syntax to make it all work right. Okay, so that's just an example of starting threads, creating threads, starting threads, joining threads. You can look at this code if you want just to see what it looks like. There were also built-in monitor object support with the original version of Java, which supported mutual exclusion and coordination, which are key synchronization mechanisms. And as a very simple example, here's the simple blocking bounded queue class. It has a take method. And as you can see, this take method, which is intended to pull something off the queue, will synchronize the object, meaning only one thread at a time can be in this critical section, everything between the open curly brace and the closed curly brace here. And with that in mind, the fact there's only one thing at a time, we can manipulate mutable shared state. So we can come in and we can say, while the list is empty, in other words, while I can't make any progress, wait, which will suspend me waiting for the list to be non-empty. And once I get through this so-called guarded suspension loop, then I will tell anybody who's waiting to put something into the queue that the queue is no longer full, if that was a condition to be worried about. And then I remove the first item from the queue and return it. And then when this closed curly brace is reached, that will automatically unlock this lock. And then someone else can come in and either add or remove, put or take into the queue. So these are very, very simple primitives for synchronization. And we'll talk more about them. You'll get a chance to play around with those and use them yourself. Now, these capabilities were very efficient. There's not a lot of overhead. All this stuff is done, sort of with hardware instructions that are built into modern chipsets. However, they're low level and they're very limited in what they can do. And we'll talk more about why that's a problem. And in particular, it's full of accidental complexities that are annoying. An accidental complexity is basically a limitation that arises due to some flaws or shortcomings with the tools and methods and languages and platforms that we use to build software. And that's distinct from inherent or essential complexities. So accidental complexities come from using sort of the wrong tools or using the tools in the wrong way, whereas inherent complexities are due to the fact that something is just complicated. We'll see later that subsequent versions of Java provide new features to work around these accidental complexities to make it a lot easier to program programs and applications that run on multiprocessors. Speaking of evolution, so 95, 96, that was Java 1. Around 2004 or so, they released Java 5. And this added a boatload of cool concurrency mechanisms, both threading and synchronization mechanisms. They added something called the Executor Framework. We're going to spend a lot of time in this class on the Executor Framework. They added a boatload of synchronizers. We're going to spend a lot of time on synchronizers. They added a bunch of blocking queues. We'll spend some time on blocking queues. They add atomics, concurrent collections. And by the time we're done, you'll get a chance to program with most of the stuff in here one way or another. So a lot more things were added, most of which, again, were written by Doug Lee. And really, really interesting features were added at that point. The focus in that time frame, 2004 or so, really was a reflection of the processing that was available. The processors were dual core, maybe quad core at best. So there was some parallelism, but it wasn't like it is today, where pretty much everybody's got quad core and octo core and hexacore or whatever, 12, 16 or more cores are becoming more and more common, even on things like laptops. My laptop has 6 hyper-threaded cores, so about 12 logical cores. Because of the fact there weren't a lot of cores in those days, they focused on fairly coarse-grained task parallelism where the computations could run concurrently. And a classic example of this was something called the Executor Completion Service, which we'll take a look at later in the class, where one or more threads can be submitting tasks to the Executor Completion Service. When a task is submitted, it's stuck onto a queue of tasks. This is all, of course, hidden from you, the application developer. And then a pool of threads running in the background will pull the requests off the queue. And depending on how many cores there are, those things may run in parallel or they may be time sliced. But in any case, things will run in the background independent of what the submitter, the client, is doing. So you get concurrency and parallelism that way. And as the processing completes in the background threads, they get stuck onto a queue called a completion queue. And then one or more threads that are under control of the client can come and take the results as they complete. So that's a good example of concurrent processing. So that was the model task parallelism that was available in that time frame. Here's a very simple example. This is actually not too dissimilar from your programming assignment, although the implementation is wildly different. This is an earlier version of the Palantir Manager application where we create a new fixed-size thread pool with n threads, 1 thread per being. We created a cyclic barrier and a countdown latch to coordinate the starting and stopping of those pools of threads, those beings. And then we go ahead for every being and we make a being and we execute this code, which basically queues it up in that thread pool. And then when the time is right, when the barrier conditions are met, all the threads will start to run and gaze in parallel. And when they're done, they'll exit, and that'll coordinate the processing between the different pieces. So this is just a simple example, not dissimilar to things we'll cover in this course, that show the Java 5 features for concurrency and coarse-grained task parallelism. There's a lot of really cool stuff in Java 5. It's very feature-rich, it's highly optimized, but it's also, honestly, a bit tedious and error-prone to program because you have to coordinate a lot of stuff by hand. Having said that, it's worth learning those features because they are essential to being considered a modern concurrency-enabled developer. So that was concurrency. Let's talk about parallelism now. So parallelism in Java didn't really come into play till Java 7, which I said was 2009, 2010. And that was when the fork join pool came along. And the focus here was on data parallelism as opposed to task parallelism that runs the same task on different data elements by applying the split, apply, combine model that we talked about before. And this was a reflection of the fact that by that time, by the 2009-2010 timeframe, more and more hardware had access to multiple cores. So there were more cores becoming available for use. Here's a very simple example. This example uses the common fork join pool to search for phrases in the complete works of Shakespeare. So if we have the complete works of Shakespeare, here, let's say this is Hamlet, Macbeth, Romeo and Juliet, Twelfth Night, whatever your favorite Shakespeare plays are, Julius Caesar and whatnot, you can then go look for phrases and it'll tell you where those phrases occur. And again, we'll use some of those examples later for other things. Fork join pool is very powerful, very scalable, uses multiple cores quite effectively, but it's still kind of tedious to program. You have to inherit stuff. You have to override these hook methods. You have to learn about all these different object-oriented subclasses like recursive task and recursive action and so on. And so it just takes extra work. It's not that hard, but there are better ways to do things. Therefore, because there were better ways to do things, with Java 8, which came out in 2014, the Java development team decided let's make it easier for people. Let's make it better for humans to program parallel platforms more effectively. And so that's where the parallel streams and completable features came in. And so the focus there was on functional programming for data parallelism, which basically kind of wraps the fork join pool with a nice functional programming facade in the form of parallel streams. And then they also added this reactive asynchronous approach, this reactive programming model with asynchronous programming. So we have asynchronous programming with reactive completable futures and synchronous parallel programming for data parallelism with parallel streams. So those are the two models there. Here's a very simple example to illustrate this point. This takes a list of URLs and in parallel gets rid of the URLs that have already been downloaded and processed in a previous run of the program, so it ignores cached images. For everything that's not currently cached, it'll download in parallel all the images, synchronously, but in parallel. And then it'll go ahead and apply image processing filters to each image, and then collect all the results up into a list of filtered and processed and downloaded images. And what's cool about this, for those of you who took the class last semester, the parallel version here, which runs really fast, by the way, on a multi-core processor, is really identical to the sequential version. All you have to do is change stream to parallel stream, and boom, everything suddenly runs much faster. So it's really cool. The conversion from sequential to parallel code is like one little tweak, one minuscule change, which is great. Here's the same requirements implemented using asynchronous processing. And what we do here is everything that says async uses completable futures to basically take a list of URLs and ignore the cached images, asynchronously download the images that are not cached, asynchronously filter and store the downloaded images, and then print the results. So this approach is a little bit more complicated than that approach. This approach is a bit more complicated to program than that approach, but it runs way faster. So that's the benefit of using these asynchronous models. They're even lighter weight and more scalable than the synchronous parallel streams versions. The trick of all these things, this is, I guarantee you, if you stay in the computing industry long enough, you will see this theme repeated over and over and over again, like watching reboots of the Spider-Man franchise or something like that, right? They keep rebooting it over and over again. There's always this trade-off between human productivity on the one hand, making it easier to write code, and computer system performance. So in theory, we could write everything in assembly code and be really fast. The computer would have very little overhead, and it would run at accelerated rates. But what a pain it would be to program that. Can you imagine trying to write assembly code for all the low-level concurrency stuff in parallelism? You'd lose your mind. Conversely, we could write everything with some kind of high-level scripting language like Python, which is arguably much, much, much easier to program than assembly code, but it might not take as thorough and scalable and efficient and low latency advantage of the underlying hardware. So somewhere between those things is the balance. Ideally, you'd like to make things easy to program and run well. So what we'll see as we get into other things, there's always trade-offs with respect to this stuff. The downside with these frameworks that have come is they can be overly prescriptive. If your programming abstractions fit nicely into the world of divide and conquer or asynchronous computations that have dependencies and so on, the world is your oyster when you use these things. If not, you're kind of stuck in a Procrustean bed of abstractions that limit you to only doing a handful of things. Anybody here know what a Procrustean bed is? Anybody here ever read any of the Percy Jackson books? All right. I have a son who was really into Percy Jackson about 5 years ago. We read them all. It actually showed up in one of the books. They go to this place and they meet Procrustes. Procrustes was an innkeeper in Greek mythology who would be offering you a free lodging, no price. You could come and stay. There was just one little problem. He had a bed, and if you were too short, he would stretch you, and if you were too long, he would chop your limbs off so you would fit. So Procrustean bed is a metaphor for kind of a force fit for something that doesn't really quite work. So it's kind of painful either way, right? Unless you just happen to be exactly right. So these frameworks work well, except when we have things that don't map onto their abstractions. Now, there's been an evolution. If you go back and watch this video, from 95, 96 to now, there's been a lot of advances and changes. And there's a really good talk by Brian Getz, who's one of the software architects for the Java platform, explaining the evolution of Java from concurrent to parallel computing over the past couple decades. And basically, if you just want the Cliff Notes explanation of his wonderful talk, he says that with Java 8 and beyond, the focus became functional programming with fine-grained data parallelism to leverage all the multiple core processors and many core processors that are coming along. And the reason for this is what happened was people thought that as the number of cores increased, right, this is the number of cores, people thought that performance would go up and up and up. But what really happened was that because it was so hard to write code using these lower-level synchronization mechanisms, the actual ability of humans, of mortals, to program this stuff was not as good as we thought. So we thought we'd get these great speed-ups, but we didn't get as good speed-ups. So they moved to the functional programming model with Java 8 to make it easier to program. There's also a nice talk by another famous guy named Rob Pike, who, in addition to being an Olympic caliber archer, I think it was, at one point, is also one of the core people who was involved with Unix, and now he's one of the main people who's developed the Go programming language at Google and the so-called Go routines. And he has a nice talk where he distinguishes between concurrency and parallelism, and I think the quote is a good one. He says, concurrency is about dealing with a lot of things at once, whereas parallelism is about doing a lot of things at once. And the main distinction there is, as we kind of talked about before, is that parallelism is about making things run independently. They can all run without any dependencies on each other. Whereas concurrency is about dealing with stuff and sharing and accessing and passing messages and so on. The distinction is a subtle one, but it's very important. And we'll talk more in the class as we get through other parts about these distinctions. Okay, so that's the end of the overview of concurrency and parallelism.